Hello, let's do some motion graphs. Okay, so I'm going to review a little bit of how to do this crazy motion graphing stuff, interpreting displacement, velocity, and acceleration, and translating between them with these graph methods of gradient, aka slope of a tangent line, and area under the curve. So, all right, this first thing is from our lecture slides, and this is the thing you got to memorize, or at least get comfortable enough with that you can figure it out on the fly. So you got to know when to do what. So if you're given an acceleration versus time graph and you want to say something about velocity, you would use this rule that the area under the curve of an acceleration versus time graph is equal to change in velocity, like over the time you're areaing. Same thing to go from velocity to time. The area under the curve, say a velocity versus time graph. For example, the area of this here triangle is a half times 2 seconds times 4 meters per second, which gives me 4 meters, which tells me that the change in displacement from 0 seconds to 2 seconds is 4 meters, which it sure looks like over here. That's what it works out to be. Okay, so area under the curve will take you from velocity versus time to displacement versus time. And then to go the other way is the one that you're maybe more used to, which is slopey stuff. To go from displacement versus time, if I have a displacement versus time graph, in other words, and I want to talk about velocity, well, I'm talking about the slope, because the slope of this graph, the gradient really, the steepness, the slope at a point, is velocity. Velocity is the rate of change of displacement in terms of time. And so by taking the slope of a tangent line on this graph, I am finding the velocity. And same deal to go from velocity to acceleration. The slope of any point on a graph, on a velocity versus time graph, will give me a value for acceleration. So those are the rules. The first thing to do is practice and study to a point where you're comfortable just knowing that those are the rules and that's what I got to do when I see these different things. That will come with practice. Again, do think about the units when you do this. Velocity versus time. You kind of do both things to this one. So if I'm not sure, if I need like acceleration, think about the units. Well, if I do some kind of slope thing, I do a change in y over change in x. I do meters per second over seconds. Will give me units meters per second squared. So that's what's going to get me to acceleration. Whereas if I do some kind of area thing and I'm doing base times height, length times width, well, then I'm going to do meters per second multiplied by seconds, which gives me meters, which is why that's going to, not really why, but that's a good reminder for which way it takes me, which is this way. Okay, so units will help. Are you dividing or multiplying? Although I should be careful because we're not dividing or multiplying really in either case. It's a little more fun than that. We're like taking slopes of tangent lines and we're taking areas under the curve. All right, so those are the rules. Make sure you know them, practice them, learn them. They will become second nature sooner or later. All right, so let's, this is just the extra practice that we looked at a little bit in class and is up on Schoology. So what I want to do is just walk through these two. All right, first, a fun one where we're given a velocity graph, and the idea here is from this velocity graph, I'm going to draw, if this is what the velocity of an object is doing over time, what would that mean about its acceleration over time? I'll graph that, and what would that mean about its position versus time? AKA displacement. Close enough for us to think about those two as the same thing. Okay, so let's do position first, I guess, since it's up top. And again, the rule is if I want to go from here to here, I got to do area. The area under the curve of my velocity versus time graph tells me the change in displacement. So let's look at how that works. To me, the thing to do would be to take the area of this first little section here, this first 2 seconds, all of this area. So, all right, to do the area, I got a square and then a little triangle. For these graphs too, these are all 1 by 1 blocks. Yeah, so I can really just count the boxes. There's 1, 2, 3, 4. I think it's going to be 5, and it will be because I got a 2 by 2 rectangle here. So that's a 4 meter area. And then I got 2 wide by 1 tall triangle. So 1/2 base times height. 1/2 times 2 times 1 is 1. So that's 1. All right, so the area of this whole section, I would kind of do all at once, or, add that up to think about this all as one thing, which is in the first 2 seconds, the displacement changes by +5 because the area under the curve here, the area, clean it up a little bit, of all of this space is 5. All right. And again, the tricky part is that this is a change. So what that's telling me is from 0 seconds to 2 seconds, my displacement goes up by 5. I'm not going to put that on the graph yet, but I'll write it over here because I don't yet know how. I'm going to have to go a little higher, I know, because I'm going to have more positive area here. So I kind of want to get my numbers before I start labeling the graph, decide how I want to scale it. I think would be the smart thing to do. Let's look at what happens from 2 seconds until over here-ish. I'm going to do a little bit of estimating. I think that looks like 3.5 to me. So I think I got a little triangle here. That's, whoa, that's like 1.5. I got a base of 1.5, got a height of 3. So the area of this triangle will be 1/2 times 1.5 times 3. Put it in my calculator. I believe I get 2.25. Again, think about the units because I'm multiplying meters per second by seconds. I get 2.25 meters, so that makes sense. So from 2 to 3.5-ish seconds, I got another delta S because that's what the area under the curve of a velocity versus time graph is. That's the rule. I got a change in displacement of plus like 2-ish, a little more than 2. Okay. Now I want to keep on going, but I'm thinking about what's happening. I'm going to go up 5 meters, and I'm going to go up another 2 meters. So I'm up at like 7-ish. All right. I'm going to kind of keep track of what my total displacement is all along the way. All right. Then, all right. We start getting into some estimating here. Do your best to estimate. It doesn't need to be perfect. So I do have some negative areas to deal with here. If I'm being really, really thorough, I probably want to count this little guy. All right, that's a little annoying. But there's a little triangle here that would be 1/2 times, I don't know, the base is like 0.5, and it's 1 unit tall, right? 1 up and down, like half this way. Half of a half is 0.25, and that's negative. Okay, whenever you're under the curve like this, when you have negative values on the graph, the area under the curve, it's unfortunate phrasing maybe, but we really mean the area between the curve and your x-axis. So it would be this area down here. You can kind of think of it as this triangle has like a negative height if you want, or just because I'm below the x-axis, this has to be a negative value. In other words, think about what the object is doing. If I'm moving with a negative velocity, that means we're moving backwards. That's all negative velocity means. And so before I was moving forwards, I went forwards, 5 meters and then another 2 meters or so. Well, now I have negative velocity, so I'm moving backwards. So I'm going to take away, my change in displacement is negative because I'm moving backwards now. And it's just this much. It's not very much at all. We can probably, you could probably get away with not worrying about this too much because this section's so small, but just to be thorough, we'll add it in. Probably good to do. Negative 0.25 meters for that little half a second there. Okay, but then let's do the rest. Next, I got this kind of area. Again, I'm going to approximate because there's some curvy stuff happening. Here's what I would do. Truly, here's what I would do. Again, these are all 1 by 1 squares. So what's the area? It's like 1 meter, 2 meters, 3 meters, and I don't know, half a meter. Let's call it 3.5. That's what I'll do. So from 4 to 6 seconds, I have an area, so a change in displacement. It's an area of 3.5, give or take. You could be fancy and do like a triangle or a square minus this triangle if you really want. I think you'd still get about 3.5. I got an area of 3.5, and it's under the curve. It's down here, so I really have a negative 3.5. Let's call it 3.5 meters. And then this last section, one more time, I'm taking the area because I'm doing the area under the curve, because the rule that I just memorized is that the area under the curve tells me change in S. So I just got to find all these areas first. That's the first step. I just kind of, have some math fun doing a bunch of areas, making some shapes, making some guesses. It's 5 wide. It's too tall. It's down under the curve. So that area is -10. And so from 6 to 10 seconds, my change in displacement is the area from 6 to 10 seconds, which is 10 under the curve, so we'll call it -10 meters. All right, so I found all of these areas of all these different sections, and the idea is all of these areas are the changes in S, the changes in my position or displacement over each interval of time. Okay, so we can kind of plot that on a graph because I'm seeing I'm up at 7 and then I'm going to go down like, I don't know, 14-ish. I'm going to end at -7 or something or so. I'm pretty confident just eyeballing these that I can go by 2s on my graph. I think if I go by 2s, I'll get up to like, I'll go, between, there's 5 of these. So I'll go from -10 to 10. I think that'll cover what I need. -6, -8, -10. All right, so let's plot these points. So the idea is from 0 to 2 seconds. That's the first interval I did area for. My position changes by 5 meters in a positive way. For the area stuff, you'll always have to be given the initial like starting value, and we'll probably always just say it's 0 just to make life easy. But this only gives you a change, so you really don't know about any of the pure values. You just know about the change. So I'm going to start at 0 because the problem said I start at 0. And then the math said from 0 to 2 seconds, I increase my displacement by 5. So I go up to 5. From 0 up to 5. That's a delta S of 5. So I'll put a point here. I'm not going to worry about how to connect them yet. That's like advanced mode. Let's just plot the points. If I can plot the points, I'm definitely at least proficient. I definitely know what I'm doing because I'm taking the area to find my different positions at different times. From 2 to 3.5 seconds, so over the next second and a half, delta S is plus 2.25. It doesn't mean S is 2.25. It means delta S, the change in S. So S, in other words, increases by 2.25. So it goes up 2 and change more. So I'm going to go up from 5 to like 7, a little more than 7, 7.25 if we're being real official. So about here, yeah, I'm eyeballing about there. Okay, then from 3.5 to 4 seconds, if I'm being real fancy, I go down by a quarter. So now I'm down at 7 meters. I go from 7.5 down to 7, so, just a little lower. Something like that looks pretty good to me. From 4 to 6 seconds, I found an area of -3.5, meaning over the 4 to 6 second time interval, my displacement goes down by 3.5. So what, 7 minus 3 is 4, minus 9.5 is 3.5? Yeah. So I'm going to go at 6 seconds, I go to 3.5 because from 4 to 6, I go down by 3.5, so 3.5 less. And now from 6 to 10 seconds, I decrease my position by 10 meters. That's, again, the area from 6 to 10 was -10. So between 6 and 10, I lose 10 meters of displacement. My displacement decreases by 10. So I'm at 3. And that means I'm going to, or 3.5. So I'm going to go down by 10. I'm going to go down 2, 4, 6, 8, 10 to like here-ish. All right. Yeah, so those are my different points that I'm going to get just by doing delta S's. So delta S of 5, delta S of 2.25, delta S of -2 or 0.25, -3.5, -10. That's the idea here. All right. So now the kind of question is, how do I connect all of these? And this is definitely the tricky part. All right, again, plotting the points, if you just get this general shape, you are in great shape. You definitely understand the core idea of how to motion graph. So like what's going to be straight lines and what's going to be curvy is tricky. The best way to do this, really the official way to do this, is to look back at your velocity graph and think about your velocity graph in yet another way. Because we want to use the rule. Let's look at the rule. We want to use the rule that velocity is the gradient of displacement versus time. So if I have numbers for velocity, it's telling me about the steepness of this graph. Just look at this example real quick. I start with 0 velocity. The velocity on this graph is represented by a tangent line, the slope of a tangent line. So 0 velocity means I start flat. I start with 0 slope, right? The delta S over delta T, in other words, the steepness of this graph starts at 0. At 1 second, looks like my velocity is 2. So I'm thinking what that means is right here, the slope of this line, that tangent line, would be 2. It's too steep there because velocity is the steepness of this graph. Velocity is the gradient of displacement. It is the slope of a tangent line on this graph. So these numbers, this is the really confusing, tricky part, but these numbers tell me the slope of this graph. The numbers on my velocity graph tell me the slope of the displacement graph, because that's kind of the definition of what it is. At 2 seconds, you know, I got a velocity of 4 meters per second. So I'm changing my displacement at this moment at a rate of 4 meters every second. So the steepness of my graph at 2 seconds, that would be a slope of 4. Okay, so you can use the velocity numbers to tell you about the slope of your displacement graph, just like you could use the acceleration numbers to tell you about the slope of a velocity graph. Look at this, constant acceleration of 2. The slope of this line is 2 everywhere. All right, that's the idea. Very tricky concept that will take some practice, some thinking, some noodling, and some doing of these problems before it really sinks in, but that's the idea. All right, so let's try to apply that. Some key things to look for would probably be when you have zeros. So for example, at 3.5 seconds, my velocity is 0, which tells me that at 3.5 seconds, this graph should be flat. The tangent line should be flat. So I'm going to have like a peak of a curve here, I think is what that's going to look like. All right, if we go from the beginning, I start with a velocity of 2 and I go to a velocity of 3. That means my displacement graph starts with the slope of 2 and goes to a slope of 3 over that same interval. The slope of the graph increases from 2 to 3 because the velocity is the slope of this graph. So it starts like, 2 steep and it ends up 3 steep, and it's like a smooth increase from 2 to 3. So the slope of the displacement graph is increasing from 2 to 3, which I think is going to look sort of like this. All right, it starts kind of slopey and it gets more slopey. It gets steeper. So it starts with a steepness of 2 and it ends up with a steepness of 3-ish. All right, and then from 2 to 3.5 seconds, my steepness, the velocity, goes from 3 all the way down to 0. So it goes from being uphill with a gradient of 3 to being flat for just a second. Right, that would be 0 gradient, because then it's going to come and become a negative slope immediately after. It's only 0 for a split second, so that's why it's going to be kind of the top of a peak. Yeah, so I'm going to kind of do something like this and come around. Now I've got my negative downhill slope because these numbers are it. And once I get to about 6 seconds, that's where I'm going to end up with a slope downhill of -2. So the slope right around here should be about -2. So it's getting more and more steep as I go until I hit this like -2 slope. Then the probably most important part that you would want to show, that you can show like the most clearly, I guess, is right here. I have a constant velocity of -2. That means the slope of this graph is going to be -2 the whole way down. Because again, the slope of this displacement versus time graph is velocity. So I really just need to make a straight line. All right, and I would definitely want to grab a ruler for this. In this case, I'll do it digital, right? But I want to get a ruler and try to draw a straight line connecting those 2 points to show that this is a constant velocity that shows up as a straight line at position versus time graph. All right, so much fun, but that graph should look something like this. Again, this is the most important part to get down first. Worry about this before you worry about any of that, which way it curves and when it's straight thing. You want to get to a point where you can plot those points on the graph using the rule about the area under the curve, giving me my changes in S. Then, once you got that down, if you get that down, then you can start trying to think about the added level of fun of these things telling you how steep this graph is. The velocity numbers telling you how steep the displacement graph is. All right, but that's the idea with that one. Let's try acceleration, which you may agree or disagree, but I find that this is a lot easier going from doing the slope stuff. Doing the slope stuff is usually easier than doing the area stuff. Usually, So because the rule is, again, think about my rules. If I got velocity versus time and I need acceleration, I'm thinking about this. Velocity versus time. To get to acceleration, I know acceleration is the slope of a tangent line on a v versus t graph. All right, slope of a tangent line will take me from velocity to acceleration. So let's try that. So I just got to take slopes. This isn't too bad. So now I'm going to think about the slopes in these different sections. All right, first part's pretty easy. There's a straight line. Let's just take the slope of this line. So I'll do the first 2 seconds. I go up 1 and over 2. So my slope, aka my acceleration, and I'll label it on the graph like that so I remember what I'm doing, is up 1/2. So it's 1/2 if I start with an acceleration of 1/2. All right, it then immediately switches. I'm going to have some kind of jump on my acceleration graph, but it switches to downhill. And what's this? I go down 2/1. So I think here I've got a slope of -2. Down 2/1, rise over run is all I'm doing for slope. And I would say that continues here and even to here. So from like 2 to 4 seconds, my acceleration is -2. From 1 to 2 seconds, looks like my acceleration is 1/2. All right, then it gets curvy. This is where there's going to be a little bit of interpretation, but all I really want to do is think about the beginning and the end. Right here, at this 3.5 seconds again, the slope is -2, and sometime later, I would say by 6 seconds, the slope here is 0, horizontal line, so slope of 0, yeah. So I'm going to say acceleration is 0 here at this point. And so really, all I care about for this, when you're doing the slope stuff, I went from an acceleration of -2 to an acceleration of 0. I can just draw that on the graph. I'm just going to connect them. Okay, so translating that down here, I'm just going to label these, let's make it easy, by 1s, because that'll definitely fit everything I need, right? I'm only going up to like -2. All right, so for the first 2 seconds, the acceleration is 1/2, and it's a constant acceleration because the acceleration is the slope, and the slope is 1/2 here, the slope is 1/2 here, the slope is 1/2 here, the slope is 1/2 here. So the acceleration is 1/2 that whole time. All right, so those first 2 seconds, I am drawing, let's see how I do with my line. I'm drawing a horizontal line. Oh boy. I'm drawing a horizontal line that should be here at 1/2 on the graph, because the acceleration is 1/2. Then the acceleration immediately switches to -2, and it looks like it does that between 2 and 4 seconds. So from 2 seconds to 4 seconds, I'm going to draw a horizontal line with my straight edge to show that I know it's horizontal and straight. And between 2 and 4 seconds, hopefully a ruler will do you better than my little tablet pen thing here, but that's the idea. Okay, and then at 4 seconds, I'm still at an acceleration of -2, and I kind of transition through. It's -2 steep here, it's a little less steep, it's a little less steep, it's a little less steep, and then it's 0 steep. So my acceleration goes from -2 to a little bit less extreme, getting closer to 0. I'm at 0 acceleration by 6 seconds. From 6 seconds on, I've got an acceleration of 0, so I'm going to do another horizontal line here at the end. And so I just need to connect them. For this, for our purposes, doesn't matter how you connect them. You could do this, you could do a curvy thing. All right, any connection would be kind of fine. So I'm just going to do this. Let's just connect them with a line, if I can make my lines work. Yeah, so connect them any kind of way. You just want to show that you understand that we're going to go from -2 acceleration to 0 acceleration, and then I end with 0 acceleration from 6 seconds all the way to the end. So there you go. There's my acceleration graph. Not as bad, I don't think. You're just doing slopes, right? Okay, there's the first one. Let's do a couple others. So, all right, again, I got 2 situations here now. I got to first think about what I'm doing. I have an acceleration versus time graph, and then looks like I'm being asked to make a velocity graph from that. Thinking about my rules, acceleration versus time. To get velocity, I'm thinking about area. So the first one, well, the one on the left, number 2, I guess, I'm going to do area stuff again. All right, so let's break this out. I'll kind of show you what it looks like. I'll try and do this one just a little quicker. Jump around, fast forward, slow down as you need to. Okay, I want to do area. Let's do the area of a nice big rectangle here. That's pretty easy. The area under the curve of an acceleration versus time graph, the rule is delta V. I memorized it. I practiced it a bunch. This is like second nature to me now. Area under the curve of acceleration versus time is delta V. The area here is what, 6 wide, -1 tall. Watch the axis here. So it's -6 meters per second, because I'm multiplying meters per second squared by seconds. Next little section, I have a triangle, and this triangle looks to me like it's 2 wide, 1 tall. So the area of that triangle, let's see, 1/2 base times height, 1/2 times 2 times 2 is 1. We're under the curve, so it's still going to be a negative answer. So delta V here is -1 meter per second. And at the very end, I'm now above the curve, so I'm going to get some positive area. It's kind of the same triangle, 2 wide, 1 tall. Watch the axis. So the area of that little triangle is delta V equals +1 meter per second. So my velocity is going to decrease to become, I'm going to subtract -6 from my velocity from 0 to 6 seconds. Then I'm going to subtract 1 more from 6 to 8 seconds. And I'm going to add 1 from 8 to 10 seconds. All right, but it's all changes. That's the big thing. So let's plot that out. And again, whenever I'm doing area, they got to give me the initial thing. So the initial velocity is 0. So we start at 0 velocity. I know I need to go down to, I guess, really -7, right? Down 6 and then down 1 more. So I'm trying to think ahead about that a little bit. And I'm going to count my graph by 2s here just so I can fit everything. Because if I just went to 5, I'd be running out of space. Okay, so we said over the first 6 seconds, was it? I go down by 6. Yep. So I start at 0. 6 seconds later, my delta V, my V has deltaed by -6. All right, I changed V by 6. Then over the next 2 seconds, between 6 and 8, all right, the interval is important. So like from 6 to 8 seconds, V changes by -1. So from 6 to 8 seconds, V changes by -1, which means it goes down from -6 to -7. And then over that last 2 seconds, V increases by 1. So from 8 to 10 seconds, I go from -7 up to this. And I already made a boo-boo because I marked my graph by 2s. So if I'm going down to 7, I should really just go here, right? So -6, -7, and then up to -6. All right, there's my points. Again, that's the important part. If you can do this, you're doing pretty good with motion graphing. You're doing quite good with motion graphing because that's, not easy stuff. All right, those are the different, velocities at different times based on this graph. Okay, now I do want to connect them, decide how to connect them. You'll get kind of used to this, but if I have a flat horizontal line when I'm doing area stuff, really. So if I have a flat horizontal line on acceleration versus time, that's going to be a straight diagonal line on my velocity graph. Because this is the slope. And what this is telling me is that for the first 6 seconds, the slope of my velocity graph, aka acceleration, is -1. So I start with a thing that's got a constant slope of -1. So this first section is going to be a straight line. So once again, I'm going to grab my ruler and try to draw a straight line connecting these 2 points, showing that I know that that's a constant rate of change here because I'm graphing. All right, the acceleration graph is the rate of change of the velocity graph. So again, this is a truly wild concept if you're really thinking about it. But the acceleration graph is a graph of the rate of change of this graph. I'm like graphing the slope of the graph on A. Okay, so then I can think about the same kind of thing. Let's see, boy, oh boy, my velocity goes from -1 up to 0 and then to +1. So that means my slope of the velocity graph starts at -1 and then hits 0 slope and then a slope of +1. So if I'm picturing that, a slope of -1, and then it gets to a slope of 0, and then it gets to a slope of +1. So I'm thinking that's going to look curvy because it's like, going through all the slopes in between too. The slope goes -1 and it's -0.5 and it's, -0.1. It's all the numbers in between, which it turns out, if you can picture this, is going to look like a smooth curve. -1 slope, 0 slope, 1 slope. So I like that. Okay. Again, that's got to be the hardest part of this stuff in a skill full of hard stuff, but that's how you would officially do that last part. All right. The next part to do is a part to focus on feeling confident about, because this one is probably more doable than that whole crazy slopey thing. All right, is to go position to velocity. So if I got a position versus time graph and I want to find velocity versus time, again, I know my rules, I've studied, and I know that I got to do gradient because velocity is the rate of change of displacement in terms of time. So I'm thinking about the slope of this graph, and I'm just going to plot the values I get. This one really not too bad. I start flat. So I start with 0 slope. Velocity is 0. Picture what this graph means. I'm at 2 meters on the meter stick, on the tape measure. A second later, I'm still at 2 meters. A second later, I'm still at 2 meters. A second later, I'm still at 2 meters. I'm not changing my position, and so I'm not moving, so velocity is 0 for that part. Same thing down here. I end at a velocity of 0. That would be a good one to just like do right away too. So I'm just thinking about overall what happens. Start at 0 velocity, end at 0 velocity. So this graph is going to like start something like this and end something like this. And I just got to figure out what happens in between. Well, what happens in between is so fun. Just think about what's happening though. It's definitely becoming negative. The velocity, the slope is becoming negative, right? It's negative. It's like very negative. It's like a little less negative. It's close to 0 negative. All right, so picturing how the tangent line, right, the steepness of the graph is changing over time is what I want. So generally, this is going to be 0, and it's like going to go down to something and then come up and be back at 0. I really just want to figure out how far down do I have to go. Okay, so how far down do I have to go? Well, I really guess then I would want to know what's the steepest that this gets. Right? I want to find I could find the slope of this tangent line to figure out how fast it's going to 4 seconds and all that. I just want to do the 1 point right in the middle though. Like how far down do we go? So the thing to do when you have something like this, to find the rate of change, I have to draw a tangent line. All right, so I'm going to have to draw a nice big tangent line from around this point. You're going to grab your ruler and you're going to draw the longest tangent. Oh boy, that's not my ruler tool. You're going to draw the longest tangent line you can that, oh boy, this is not going to work super great, is it? You want the longest tangent line you can that more or less goes through and just hugs that point. All right, that's actually not too terrible. Yeah, okay. All right, we can work with this. All right, so I got a tangent line here. This tangent line is going to tell me the velocity right at that point, right at the steepest point of the graph. All right, definitely do a ruler when you do this. You'll get a much more accurate answer. Okay, so we'll see how close I get with this little digital tool here. But I want to pick 2 points on the tangent line now. Ideally, 2 points pretty far away from each other. So I've got, this is a good one for sure, 7, -5. And then, I don't know. I don't have much grade up here. I could probably pick this point. I don't love this. I would prefer something up here, but it crosses pretty well right there. So let's try it. I got 4, 2. Okay, so if I do rise over run, if I do change in y over change in x, the slope, the velocity there is going to be y2 minus y1, -5 minus 2 over x2 minus x1, 7 minus 4. So what's this? -7 over 3, so -7/3. So 6/3 is 2, so like -2.3-ish. That's good enough. All right, a little less than 2, -2. Is about the slope there. So the velocity, again, is what I'm doing, is what I'm thinking about. Velocity is 0 because the slope is 0. Velocity becomes some negative number, some more negative number, some more negative number, hits -2 point something, 2.3, let's say. And then, like, depending how you think of it, I guess officially increases, gets closer to 0, right? So at some point it goes from -2.3 to like -1 to -0.5 and then to 0. So that's all I got to draw on my velocity graph, is something that starts at 0, eventually gets to, let's label these up, -2.3, and then 2, 3, 4, 5 goes back to 0. All right. I would say it's at that maximum negative velocity right in the middle, right at 5 seconds. So the first point I might plot is just that -2.3. Okay, the tangent line tells me that at 5 seconds, roughly here on my velocity, -2 point something. And I started at 0, I ended at 0. Now I just kind of got to decide, and there's a little bit of estimating and interpreting here. There's not an exact right answer. So it's 0, the velocity is 0 for definitely the first 2, probably 3 seconds, maybe 2.5, 2 and change. Let's just call it the first 3 seconds, I think is good enough. It's pretty much flat there. And it's pretty much flat the last 3 seconds. All right, it's really just about getting flat for the last 3 seconds. So let's say it's 0 for the first 3 seconds, 0 for the last 3 seconds. That's going to be good enough for us. 0, 0. All right, I should use my straight lines. So let's use my straight lines for that part. And then I really just can do my best to guess what I think this is going to look like. This, when you're doing the slope stuff, it doesn't matter too much how you draw this shape. You can do your best to guess, but all I got to really show is it's going to go from 0 down to negative 2.5, and then, or 2.3, and then back up to 0. So something like this would be fine. You could also guess, and would probably be right if you did something more like this, because all the change is happening really close to 5 seconds or something. All right, but anything like that, or again, like, down and then back up would be all good. Okay. All right, so there are 2 examples in gory detail to hopefully help walk you through this extra practice. And again, it's really just about getting these 2 rules down. So knowing when to do area under the curve and when to do slope of a tangent line, and then applying those to try and draw the other graphs. Okay, so keep at it. It takes a little practice until you get used to these, but those are the rules. That's how you use them. So hopefully this helps a little bit with your motion graphing fun. See ya.